any point, just let me know, or if I need to go back. You will want your graphing calculator today as well, because we're going to do some graphing stuff. So on Tuesday, we talked about inverse functions. Example 1, you were finding inverse functions by switching our x and y, and then just solving for y. And example 1 was more simple functions, so they were linear functions that don't have a power. Example 2, we were verifying inverses using composition. Yeah. The what? Oh, once it's in your photos, hit a plus. And then like look it up. Huh? You just look it up. Yeah, if your airdrop's not on, go to Safari, and I just search link coordinate grid. And then usually this first one's nice. You just hold down your finger on it and hit add to photos. So today we're going to talk about finding inverses of power functions, so functions that have an exponent. And then we're gonna also graph f and f inverse on our graphing calculator, but I want to draw them down here then. So example 3a, I'm looking at f of x equals x squared, and then I have this funny thing over here, where x is greater than or equal to 0. What this is your domain, and you're going to see this sometimes when your power is even. So even powers might have domain. And I'll talk more about what that looks like tomorrow, because I need to do a little refresher on domain range. So in terms of finding our inverse function, the domain doesn't matter for that. We're good to just, remember if it's in function notation, it's easier to switch it to y equals x squared. And then we want to switch our x and y. And you're literally just going to switch the x and y. So this becomes x equals y squared. Notice that the square needs to stay on the y now. Okay? It stays with wherever it was. All right, then our rules apply that in order to undo the square, we're going to take a square root, but you have to make sure that whatever's being squared is by itself first. This time it is, so you're good to take a square root of both sides. So you'll have the square root of x equals y. And we can rewrite this, if we want to use function notation again, we can rewrite this as f inverse of x equals the square root of x. I have this entered like 3 different ways for your Go formative practice. You can do f inverse with that -1 power. You can do y equals whatever the function is, and then you can actually just do the function too. I have it entered all of those ways. Any questions about finding that inverse? All right, so the fun part, graphing it. I know you love graphing. So we can resize things if we need to here, which is nice. I'm going to do our original function, so our f will be in red. And I'll do f inverse in blue. So it's still easiest to make a table and just plot some points here. So on your graphing calculator, for our original function, we have y equals x squared. So on your graphing calculator, go to your y equals, hit clear if there's something in there, and then type your x, which is next to the alpha button, and then you can either use the caret or you can use that x squared in the first column. So we have x squared, so our y equals x squared. Hit second table. We can still look at the graph too, but remember if you hit second and then graph or second table, you get this nice table. I use this one for that's your short cuts. And then hit second. All right, so once we have our table, notice our axis of symmetry is at 0, so it starts repeating around that 0. Really, we just need 1 point on either side, so we don't have to make our table too excessive here. Because we've been graphing for a while now. So 0, 0. At -1, we were at 1. At -2, we were at 4. 1 we're at 1. 2 we're at 4. Okay, this is where the domain comes into it. Your calculator, there's no way for you to put in the domain for your calculator to know what to do here. But remember, the domain said x has to be greater than 0. So what you're going to do here is you're just going to cross this off. You're going to get rid of those negative values entirely. So when you graph this, you're really only going to have half of a parabola. You have a point at 0, 0. You have a point at 1, 1. You have a point at 2, 4. Technically, you have a point at 3, 9. Go ahead and graph that. Okay, so that gives us our original function. Let's graph our inverse now. So go back to your calculator, go to y equals again, hit clear. Go to y equals and hit clear. If you're in your table, you can hit second quit. Go to main menu and then hit y equals. And then we're going to do our square root. So it's the second button, that blue button. And then it's the same place that this x squared is, right? It's in that first column. Move the square root. And then your x. All right, then you can go to your table again. Notice now, our table, we have errors at x equals -1. So our table really is just going to be 0, 1, and then we have a bunch of decimals. The only other point is 4, 2. So those are going to be the points that I plot. I'm not going to plot those decimals just because it's a little too much. So I am going to say that -1 is an error, just so you remember why we're not putting those in there. At 0, we're at 0. At 1, we were at 1. And then at 4, we're at 2. The rest are all kind of crazy decimals. So I can graph 0, 0, 1, 1, and then at 4, I'm up to 2. Recall that on Tuesday I said inverse functions, the graphs, are reflections over the x equal, or the y equals x line. And you can see that here. This dotted blue line is that y equals x. You can see that these are reflections over. So like this is the same distance as this. You guys see that? Think of that dotted blue line as a mirror and then the reflection on the other side. So that's just this kind of a verification that in fact that's true. And we can see how our bounds work then, because this half, if this half had been here, it would have reflected like that, which is a problem. Let's see why in a second. Any questions about that? Okay, so part B, we have f of x equals 2x to the third plus 1. Notice this is an odd exponent, so there is no domain here. I mean, there is a domain, but we don't need to specify anything because really what the domain is our domain is just negative infinity to positive infinity. So since that's our domain, it doesn't really mean anything for us. It doesn't mess anything up. We're kind of just good to go. So I'm going to start by rewriting this in y's and x's. Y equals 2x to the third plus 1. And then switch your x and y. So we'll have x equals 2y to the third plus 1. Okay, I want to take a third root to undo that third power, but before I do that, I need to get this y by itself. So I'm going to have to do some stuff. I'm going to subtract by 1 to start. So we have x minus 1 equals 2y to the third. I'm close. It's really tempting to try and take a cube root now, but don't take the cube root of a 2. Let's instead get rid of that 2 by dividing by 2 on both sides. So we have x minus 1 over 2 equals y to the third. Now that y is by itself. Tuesday we said we'd split these. Don't split these for power functions. It looks neater if you keep them together. If it's a linear function, yeah, split them because then you can simplify. But for the power functions, just leave them. And we're going to go ahead and take a third root on both sides to undo that third power. So we'll have x minus 1 over 2 all to the third power, third root, equals y. And I can rewrite this in function notation as f inverse of x equals the third root of x minus 1 over 2. Any questions about getting that inverse? Yeah.
So the y just turns into the f inverse?
Yeah, that's stuff. And again, on GoFormative, you can leave it as a y, that's fine. But I do want to make sure you guys understand that f inverse notation. Alright, so graphing these. Again, I'm going to graph my normal function will be red, my original function, not normal. My inverse function will be in blue. I'm trying to record that later. Alright, so for my calculator, for the original function, go to your y equals and hit clear. Y equals and hit clear. Then type 2x. And here you'll have to use the caret button that's under the clear button to the third power. 2x, that little arrow button, third power. And then scroll to the right so you get out of the exponent, plus 1. 2x to the third plus 1. You can hit second table. So in our table, we have, there's not going to be an axis of symmetry here. So I'm just going to graph negative 2's at negative 15, negative 1's at negative 1, 0's at 1, 1's at 3, and then 2's already up to 17, which is bigger than what we can do that. So when I make my table in the notes, I like to put those ones that I can't graph. So we have negative 2, negative 15, negative 1, negative 1, 0, 1, 1, 3, and 2, 17. So again, if you guys remember from first semester, those ones you can't graph can be kind of like guiding arrows for you when you're graphing these. So I'll start in the middle. 0's at 1, so at x equals 0, I'm up to 1. At x equals 1, I'm up to y equals 3. And then at x equals 2, I'm at y equals 17, which is off my graph, but at y equals 2, I can put like an arrow there to help me guide where I need to go. That where is something.
Did you graph negative 1 and
Negative. So at negative 1, I'm at negative 1. And then at negative 2, I'm already down to negative 15, so that arrow will go there. Oh my gosh, I can't escape the glare. Alright, so this graph looks something like this. Huh? Because of that domain. So why didn't I graph the negatives on the last one? Because it had this domain. And there is no domain written here. Because it's a third power, so it won't actually matter. You'll often see it with an even power. I don't think you ever see it with an odd power. Alright, so now we have to graph cube root. This is the one where you're going to want to go. So you go to your calculator, hit y equals in your calculator. Hit clear. Alright, now we have to go to our math menu because we want to graph the third root. So if you hit your math menu, you have two options. You can either go to number 4, which is the third root, or you can go to number 5, which is your nth root, so that's any of the roots. If you go to number 5, just make sure you then fill in that it should pop you into that root part. It's math, it's under the green button. So you have your third root. And here you're going to have to use parentheses. Once you have your third root, you need to put a parenthesis, x minus 1, close parentheses. So, parenthesis, x minus 1, close your parentheses, and then put divided by 2. If you don't put the parenthesis, your calculator is going to think you're inputting x minus 1/2. So that's why you have to do x minus 1 in parentheses all divided by 2. Once you have that, hit second table. And look at this ugly table we have. So, we do have a point at -1, -1, and we have a point at 1, 0, and we have a point at 3, 1. But the rest are sort of a mess. So, it's enough to just graph it based on those 3 whole numbers, but let's go ahead and, if you just hit graph, and look at this graph, so that we know where to point our arrows. So it's going off to the side, basically. It's not quite a horizontal line, because this is a function, but it's pretty close. So in our table here, we can graph -1, -1, we can graph 1, 0, and we can graph 3, 1. So at -1, I'm at -1. At 1, I'm at 0. And at 3, I'm at 1. And then just kind of know goes off this way and down. And again, that blue function is the inverse, so it should be a reflection over y equals x. And if you graph that y equals x line, you can see that is a reflection over that point, or over that line. Any questions about this one? Okay, I'm going to skip part C for today. We'll do that tomorrow, just because I'm going to run out of time. Otherwise, I won't have time to work on this after home. But let's look at example 4 now. So these last 2 examples took a lot of time, right? And math people are like, nah, we're not going to do that. That's too much time. We're instead going to create this horizontal line test. So do you guys remember the vertical line test? The vertical line test says, if you have a function, so I have 2 functions here. This is actually part A without the domain. If you have a function and you draw vertical lines anywhere on that graph, it should only cross the function 1 time. So if you look here, I've drawn some vertical lines on these 2 functions. Ignore the dotted red line, that's our y equals x. So the purple function is our y equals x squared. So this is y equals x squared. And the blue function is that y equals the square root of x. Technically, the blue function, because I really should have put this in the original part, is plus minus that. Notice that the purple function passes that vertical line test, right? It only ever crosses the purple function 1 time, it doesn't hit it twice. But the blue function, the vertical line test, fails. Meaning that this blue function is not a function. Unless you have bounds on it. And that's why in part A, we only graphed the top half of it. And that's why you often have these domain limits on these in order to make the inverse be a function. But mathematicians were like, that's still too much, that's too much work, that's crazy. So instead of doing a graph, and then finding the inverse and doing a second graph, and then seeing if it passes the vertical line test, it's enough to say say that if this function here passes the horizontal line test, meaning if you draw a horizontal line and it hits 2 times, that means it doesn't pass, then obviously its inverse, that reflection over the y equals x line, also won't pass the vertical line test. So mathematicians came up with this shortcut. It's called the horizontal line test. And again, horizontal line, think of the horizon where the sun rises, right? It's that side-to-side line. So this says that the inverse of a function f is also a function if and only if no horizontal line intersects the graph of f more than once. So if we look at those 2 examples above, these both pass the horizontal line test, the original red function. So obviously that blue function would pass the vertical line test. So that's going to be our shortcut here, is that you're just going to graph the original function and see if it passes the horizontal line test. I want to stress to you that if a function doesn't pass the horizontal line test, that original function is still a function, but its inverse is not. So you have to watch out for that. So example 4, and again, we're just going to do part A and C, and I'll save B for tomorrow. Example 4, we're going to graph the function f, and we're just going to determine if the inverse of f is a function. We're not even going to find the inverse of f. So for part A here, this is actually just a linear function. Hopefully you remember how to graph these. Y equals mx plus b, where b is your y-intercept. So if you go up to 4, that's my y-intercept. And then my slope is 2, meaning go up 2 over 1. So from that y-intercept, up 2 over 1, up 2 over 1, up 2 over 1. So this is my function f. My horizontal line test says I should be able to draw a horizontal line anywhere through this and it only touches the function once. That is true here. So we can say f passes the horizontal line test. So f inverse is a function. On Go Formative, literally all you have to put is yes or no. So this would be a yes. You do have to have the graph of the function, so it will auto-grade to correct, but if you don't have a graph, I'm going to go back and manually change it to wrong. Any questions about that one? Or about the horizontal line test in general? All right, so part C, I really want to do part C because I am betting you guys don't know how to graph absolute values in your calculator, so let's talk about that. So part C, we have f of x equals the absolute value of x plus 2 plus 1. So in your graphing calculator, go to y equals, hit clear. Y equals, hit clear. Then you're going back to your math menu. In your math menu, so once you hit math, you're in this math menu, you have to scroll to the right 1 time. It's actually in that number menu. So scroll to the right 1 time. And then it should be that first option. It says ABS, that's absolute value. And you just hit enter. You're either going to have ABS parentheses show up, or you'll actually have the absolute value bars show up, depending on what your model of calculator is. So if you have the absolute value bars, you're just going to type in x plus 2, and then scroll out of that absolute value. If you have the older calculator that says ABS with a parenthesis, at this point, close your parentheses. So you have x plus 1, close parenthesis, and then put plus 1. Means that 1 is outside of the absolute value. Anybody having trouble with this? Everybody find it? Okay, so here, let's look at the graph real quick. Notice it's like a V. This is why I don't like it when you guys draw parabolas that are like super pointy, because actually that's an absolute value function, not a square. But this one should be pointy, so if you look at your table, we have values, it's sort of centered, so our axis of symmetry is around -2. At negative 2, it's at 1, and then at negative 3, it's at 2, and negative 1, it's at 2. So that's where it starts repeating. So if we make this table, part C here. X, Y, make this table at negative 2, we were at 1, so at negative 3, so at negative, we're at 2, negative 1, we're at 2, at 0, we're at 3, and at negative 4, we're at 3. That's just from your table. So when I graph these points, at negative 2, I go up 1. Then at negative 1, I go up 2. At negative 3, I go up 2, so on either side. At 0, I go up 3. And at negative 4, I go up 3. Alright, so this is my function. If I want to see if this passes the horizontal line test, I draw a line through it. It does not. It's that function 2 times. So we would say f does not pass, I'm going to abbreviate, the horizontal line test. So f inverse is not a function. In order for f inverse to be a function, we would have to tack on a domain to our original function. And again, we'll talk more about that tomorrow. So endoformative, you just put. Any questions about that? So we'll finish up these 2 tomorrow.